Thank you very much, Manas. My name is Syed Ahsan. I'm going to be presenting our work towards the development of microwave tomography system, along with my colleague Yannis. So the outline of this presentation is, first I'm going to talk about the system design requirements and challenges, in which I'm going to talk about the different components that we have in the system, and then we will talk about the two imaging setups that we have. And then we will discuss something about the phantom fabrication and the future work. The approach that we are taking towards building this hardware is we're designing everything in a software model, 3D software model. It's commercially available, CST, and then we are validating it with the experimental setup. And ultimately, our goal is to go towards user-centered design. So in terms of system design requirements and challenges, the first and foremost thing is the antenna design. Now, antenna has to operate at a specific frequency based upon the requirement. And as Francesca mentioned, and in the motivation, we knew that we need a smaller frequency range for the better penetration and higher frequency for the better resolution. And also at the frequencies where the dielectric contrast between the materials is larger. So hence we need an antenna that operates in the desired frequency range, which essentially is 0.5 to 3 gigahertz roughly for tomography purposes, and for radar-based applications it's a bit higher in outer wideband range. Then the second step is to develop a phantom, which is going to be optimized for the better transmission, because that's another issue, how to couple the energy, and we use dielectric medium to do that. And then I'm going to present the CST simulation and experimental results. So antenna design is very frequency dependent. At the same time that we are dealing with an ill-posed problem in microwave tomography. Hence we need multiple antennas. So this means that this antenna doesn't only operate in that specific frequency range, it has to have a smaller footprint as well. So the dimension has to be very compact. Again, when we design a compact antenna and we put multiple antennas in a system, there is another issue that arises, that's the coupling between the antennas. So in order to reduce the coupling, which is an unwanted, undesired characteristic, we introduce the lossy liquid in between. By introducing lossy liquid brings another challenge. And that's the signal-to-noise ratio, which is by ordinary hardware. If we attenuate the signal too much, we cannot detect it, and hence we cannot process the results. So we have a lot of work to do on optimization of the dielectric medium that we're using to couple the energy, design the robust antenna, so it's repeatable. It's going to be working in a different environment, sometimes in the free space, sometimes in the lossy liquid. So it has to be very robust and compact, obviously. So I'm going to introduce the antennas that we've designed so far. We've designed three different antennas for this application, two triangular printed patch monopole antennas and spear-shaped antennas. We've measured the results. The larger triangular antenna, which is about 24 by 30 millimeter, it operates best at the frequency 0.9 gigahertz. The smaller antenna, when immersed in a 90% glycerol, operates best at 1.8 gigahertz, and it's almost half the size of the larger antenna. Then we have a spear patch antenna, which we are currently investigating, and that also has a small footprint, and it works best around 1.2 gigahertz, and we've measured this performance. But we've also worked on polyester fabric substrate antenna with our collaborators in China, and that antenna will also be tested, and that shows good S11 characteristics between 1.2 to 4 or 5 gigahertz. Matching the dielectric medium or any other to the tissue to couple the energy is a very challenging task. So we can do either by using the liquid or bringing the new metamaterial technology into it, which I'm not going to talk too much about. Thomas from Mediwise has a complete presentation on this subject. So how we approach the problem is we use CST software to model our system. Here is an example of the system where we are using the SAM model from CST, which is a software model for head, and we create multi-layers in it. And we're surrounded by the liquid, which is the matching liquid, which we're going to use in the experiments as well, and use the acrylic tank to enclose the liquid in there, and then In order to isolate and mitigate the surface wave and multipath signal propagation, we surrounded by the absorber and the metallic sheet. So there are different configurations which we studied before approaching the design, and in which, in one case, we are considering the small pouches where we put the immersion liquid and the antenna, and we surround the head model with those pouches. And then we introduce a blood sample, which is this red clot here. And then we also studied the effect of these antennas operating in the free space around the head model. These are the field distributions that we obtained after running the simulation in CST model. And as we can see that if the whole antenna and the setup is immersed in lossy liquid, we have lower signal, but we have very consistent response in terms of the received signal at different receivers. However, when the bags have been used, so we have air interfaces in between, so we have a lot of surface waves which go around the head model and are received at the different antennas. And the same goes for the headband as well, which is slightly better than the bags, but not as good as the fully immersed cylindrical geometry. Now here is the propagation of the signal, how the fields are distributed when the antennas operate in the free space. As we can see that the high strength of the field is around the head model. Now here's the reconstruction result of this simulation setup using the DBIM twist method, 2D. And this reconstructs the epsilon infinity, which is the dielectric parameter of the object that we are investigating. So, and it has located the object in the correct location. Now we have two imaging systems, radar-based as well as the tomography. And the reason we have two is in the long run we will try to merge the two to create a hybrid algorithm. These are the results from some previous work on using these two methods, in which we've successfully reconstructed the images, any discontinuities from the simulation data. A radar-based imaging setup is comprised of a very simple setup where we have two antennas in a circular geometry, and we manually rotate the antennas. For 4 antennas, we have 24 receivers at each location at a step of 15 degrees. And we do this task manually, and this system is capable of operating in the free space as well as in the dielectric medium. And these are the results of reconstruction when we put a water target at a known location, and we acquired the data by giving it 4 transmitter locations and 24 receivers, and both in free space and with the inclusion of dielectric. Our tomography setup is comprised of 8 antennas, and that also has acrylic tank in the same, but it works only in the dielectric medium. So we have some vertical mounts which are there to adjust the position. So this system is quite flexible in order to acquire the data for 2D or 3D imaging setups. And there is a very robust system in place to insert different targets in there. So here is an example where we have a cylindrical cylinder which has 4 inclusions in there. So we can actually put 4 different targets with different sizes into it, and to perform the measurements, so to have like different contrast and different materials in this. Now this is the VNA device that we've recently built, a 8-port system, and all our antennas work at the same time using this device. Now here are some examples of the simulation and experimental results that we've performed previously using the small antenna that I presented earlier. On the left-hand side, we have the cylindrical water target, and these are the results from the simulation data that we acquired from CST. And on the right-hand side, we performed all these experiments using the setup that I presented earlier. And we found the target in the exact location in all cases. Here is the 3D reconstruction, which is a slightly excuse me, different algorithm, but we have the same setup to acquire the data, and we applied 2D and 3D reconstruction algorithms for a short cylinder, which is not fully vertically aligned with the material. However, it's 4 centimeters. It's like a limited length, and we've obtained good results in both cases, 2D and 3D. And this one here, the one on the far right, is the 3D case from the side view, which shows that it actually reconstructs only along the length, which is 4 centimeters in this case. The phantom fabrication measurement results are going to be presented by my colleague, Yannis. Thank you.
Thank you very much. Thank you. So I'm going to talk about phantoms and tissue mimicking materials. So we have the need to be fabricating phantoms because we cannot go into the human trial early on whilst we validate our system. So we use hydrogels that closely emulate the electrical properties of human tissue. These are, for instance, blood, the brain hybrid that we use in an average for this point. That is an average between gray and white matter. The cerebral spinal fluid and the skull, as well as the scalp. On the right, we can see also there's a 3D printed ellipsoid that's very close to the brain size. So this is a 3D printed model that is inserted in the middle of the tank, showed here. There are several layers that we can actually disassemble and add different mimicking materials. This is placed in the center of the tank, and as described earlier, we can move the antennas on the horizontal and the vertical plane, as well as rotating them around. This is a top view of the system. Also, more detailed design on how modular this multi-layered phantom is. So we have several caps, one inserted into the other, that if you turn it the other way around, you insert the liquid, you push the next layer, and etc. You can build up a more complex scenario. We'll talk about more of this in the next slide. And basically, here's the fabrication, how we managed to add the target, the insertion in the average brain. So the average brain is on a permittivity of 42 as we fabricated it. And this is the white part inside the bigger ellipsoid. We have located the target on a distance of 30 by 30 from the center of it. We've used an insertion, 3D printed jig, I would call it, so we can remove the average brain part from that specific area, and introduce the hemorrhage target of 68.5. So yeah, we call it as a target. Of course, it would be closer to the hemorrhage, and maybe at this point it's better to show how this is made. So these are the targets here, as well as this is a 3D printed plastic ABS part, where we have two targets, one on the left that is 15 millimeters and the other one that is about 40, sorry. This will be included in the anthropomorphic phantom that we are working on. That's still on a CAD model and 3D printed. So when we are fabricating this, the dielectric measurements at 1 gigahertz, as mentioned earlier, are here. You can see that the fat gray matter CSF is quite high, very close to the hemorrhage. We tried to fabricate the CSF. That was quite tricky on the outer layer of the ellipsoid. So we use the molding technique to push down the liquid and let it solidify. So after that, we remove the black piece, and then we add the average brain, so we can see how much the CFS influences acicular penetration. We're also using a slim probe kit on the 8-port Keysight VNA, and we're performing measurements so we can see the line in the frequency that we want, from 0.5 to up to 2.5. We see that we managed at 1 gigahertz to get very close to the reference data of CSF. And also we use a secondary probe from another 2-port system to measure the average brain. A bit more regarding the measurement. So once we've fabricated it, we need to measure it, make sure that the values are the same on that day and also 3 or 4 days after, so we can continue measuring with different approaches, different antenna rings that I would like to describe now. So this is a top view of the experimental system with a circular ring of antennas at a certain height, as you see here. We are varying the heights of the antennas, and we also change the array of the antennas. One is the cylindrical approach, and the other one comes closer to the ellipse, so it creates an elliptical array that has been giving us a bit better data. You can see also the target is at the black point inside here, and the tank is filled with 90% glycerol up until 20 centimeters above the phantom. So here there's, sorry. So here there's a small video. I don't know if it's going to play. Let me try. Nope. Okay, unfortunately this won't work. So basically, we could illustrate some iterations. I can show it to you outside where we have the demo. The iterations for the reconstruction of what the data came out from the experimental results for average brain and the hemorrhage on that specific point. We could see that in the area here, the antennas could, the algorithm could actually see the hemorrhage. So I'll go into next steps and some future work. So this is a CAD design still. It's anthropomorphic SAM model provided us from CST. It's a more complicated for us approach for now. It's not really complicated. However, we would like to validate a helmet, a hemispherical helmet of 24 antennas that are in 3 layers. So it's 12, 8, and 4 antennas that will be adapted and conformed at the exact position of the head. So we could make models from molds that this would, for example, emulate the skull, the average brain, as well as the hemorrhages in some specific areas. This will be prepared exactly the same method described earlier, and the helmet will be 3D printed, and each antenna will be inserted in a special case that I will describe later. We're doing this because we want to verify our experimental data and have the minimum errors. So validating simulations with experimental results. So more to discuss a bit more on the anthropomorphic SAM model. Again, the preparation of the targets can be shown here, that we have already done. These are the cylinders, and here's the sphere. I haven't shown it. It actually will be fitting inside this area. This is 30 millimeters in diameter. The cylinders are 60 and 30 with a height of 30 millimeters. We would like to keep this as a reference, and the model is used again, exactly the same model in the simulations. And here's the 3D printed part. This has a cut on this direction. We're also thinking about making a cut on this direction, so we can make a full model and be able to add the targets inside. So yeah, this is an idea of the matching medium inclusion for enhancing the antenna performance. So rather than submerging the antennas into a matching medium of glycerol 90%, we could actually make a phantom with the same properties and pour it inside these areas in the case. Once it's solidified, we remove the front part and we can adapt the whole casing with the antenna around a headband. So this is a different concept, having only one array of 8 antennas. Looking at the final microwave imaging system, there's work done from design on the antenna arrays that's been done in King's. Actually, lots of stuff has been done from both sides, but basically the design of the only one signal transceivers is by collaborators in China, as well as the prototyping and testing and the optimization of the hardware and the actual helmet. The imaging algorithm, as we described earlier, is also work that we have been doing here. And the current system in China, it comprises of, this is the system overview, where you can see here also the platform with the 8 antennas. There's a movement from, I'm not sure, yeah, actually there's all the antennas. There's no movement on the z-axis, but on this axis. The switch matrix, also described earlier from Francesca Fipiana, and here's the VNA with the PC that controls the unit. So, yeah, I'd like to make the acknowledgements to all the team that's been working on all this project. So it's Syed, Navid, Mohammed, Zuen, Pan, Wei, Olivia, Leonora, Elena, and Maria, Zheng, and Wedding. Thank you very much for your attention, and if you have any questions.
Thank you very much.
Thank you.
Okay, so we got to lunch, which is great. It was a long, but then maybe one question, then we can also have discussions over lunch. Yes, Francesca.
Okay, I have more a curiosity than a question probably, because as you have seen, we are also working on similar ideas to build a helmet around. And one part that is not easy to be done is to have really the antenna conformal to the head. So we realize that with blocks of dielectric that is not incredibly rigid, but not so soft that can be conformal. So here, yes. So the question is, the gel matching medium that you are using here is something so soft that can be adapted to the head, or once you do the not flat head is already considered once you are doing the casing?
I've created a small curvature at this side. You can see it also outside. I brought it so I can demonstrate. Okay. So basically, once you have filled in this with the phantom, there will be a small area exactly at this curve that could be more soft to adapt on the head. Okay,
so it's not, I mean, you start not from a rectangular size, but it's already,
no,
okay.
So it's already like that, but we haven't measured this yet. It might need to be much bigger.
But this, I mean, I think in our opinion is okay. You have to measure to check the electric properties, but it's more a mechanical problem. So you should be able to place the antenna.
I'm taking it from a different. I'm putting it from a product design approach. Putting this as a priority and see how it works, and then try to work from there. So it's I'm going back rather than this side.
Okay, thank you.
Yes.
Just wondered how easy it was to get the helmet on. I'm thinking about it. Someone who's had a brain attack, can't move their head, can't swallow.
Yes.
Have you tried it in different types?
I would say that this wouldn't be the final solution. However, for the Phantom that we would like to build, I would use it as a reference. I think this would be like a way to start complicating things. However, the final design, it will be much trickier. And defining the geometry of each antenna, where it is for a wearable, it's always very tricky. Yeah.
Okay, thanks for this comment. Any other comments, questions? Yes, sure.
What is the impact of airs?
Between the antenna?
The airs.
Between the hair. Do you have no this?
No, we haven't measured it yet.
No,
There is a paper.
yeah.
There are people looking into it, but yeah,
We
haven't
won't
done it
include
yet.
Yeah, we
Yeah.
haven't done it.
Yeah.
We'll
Well,
put a
in
wing
China,
on.
you saw the Phantom has hair, so maybe when they can say something about that. Yeah.
Okay.
Thank you again very much. Thanks to all the speakers for this first part, and we have lunch in the same.